Hello again, my name is Jordan Deshawn, and we've reached the final step, step 5, solar. The question to address here is what solar array design is needed to supply the power required by the pump, which is what we determined in step 4. And first, under step 5A, we're going to look at our solar panels and some of the project conditions. And first, we'll define the brand and model of the solar panels that we'll use in this project. Based on that information, we want to then enter the solar panel specifications at standard test conditions. You can find this data either on the sticker on the back of your solar panels or on the manufacturer's website. You can find that just by searching for the brand and model number and trying to locate a PDF or on the website find the specifications that give you this information. Next is the project location and some of the solar array design. So we can see the design engineer has entered the latitude and longitude coordinates for this project location. And then we specify the slope of the solar panels. And we see here a minimum of 15 degrees is typical or recommended. Next is the azimuth, and that's the direction that the solar panels will point or face. And finally, a design month, which we usually want to choose as the lowest solar irradiance month. In this case, it looks like it's January. Now you might be wondering, well, how do I determine the lowest solar irradiance month? This is where we can use the Photovoltaic Geographical Information System, or PVGIS. We can also get the daily irradiance and temperature for each hour of the day on this website. So let's click this link to go to PVGIS. So this will take us to the PVGIS website where we could get irradiance or temperature data from any location in the world. You can either click here in the map or you can enter your latitude and longitude coordinates. I believe the latitude and longitude for this project are -8.98, so it's going to be in the southern hemisphere, and 117.7, and then we can click go. Once there, you could zoom out, and we can see maybe these aren't quite accurate because we ended up in the ocean here, but it's pretty close. If we wanted to, we could click somewhere on the land or just zoom into your project location. Next, what we want to do is adjust the slope and the azimuth. Since we're in the southern hemisphere, we want to point them north, which is an azimuth of 180 degrees. After that, we can click Visualize Results to see which would be the lowest irradiance month. Looking at this, we can see it might be December here, but maybe that's just because I adjusted the location slightly. But our design engineer has chosen January as the lowest irradiance month. Once we've selected the lowest irradiance month, we can click on the Daily Data tab here. Choose that month, in this case January, select local time, and then check these two boxes for irradiance and temperature, because that's what we want to see. Change our slope to 15 and azimuth to 180, and then click Visualize Results. There's two options to get the data from this curve. You can download the CSV file or click on this Print PDF option. Let's try this Print PDF option and open the PDF here to see the data. So here we can see it gives us the global total irradiance for various hours of the day, and then the temperature. Instead, let's try to click on this CSV button to download this CSV file. And I'll quickly go through this. If you need to, you can pause this video to follow these steps as I go through. So we've opened the CSV file. I'm going to select the entire column A, click on the Data tab at the top, and then click this button, Text to Columns. I'll then click Next, Next, Finish, and it's okay to replace the data here. All right, so we've gotten information on the irradiance. It looks like the temperature isn't giving us temperature, so we might have to work with that. And then for the local time, here we can go from 6:30 to 7:30. And we could then just copy this data and paste that into our tool. We can see here the design engineer has already done this for the location and done the same for the temperature. If you have any questions about this step in the process, there's a helpful guidance document that can walk you through how to get irradiance and temperature data from PBGIS. Next is the power output section. And the main things to define here are the number of panels in series and then the number of parallel strings of your array. There's an optional calculator tab you can use to see what the recommended numbers for these would be, or estimate your solar array configuration. Here, the design engineer has chosen 6 panels in series and 3 parallel strings of 6 panels each. And then we can see this automatically calculates the power output from a single solar panel and the power output of the full array. One of the close things to examine here is to make sure the array VOC does not exceed the pump's maximum allowable voltage. We can see here that if these cells turn yellow, it means the array VOC exceeds the voltage, but it may be acceptable in certain situations. If it turns red, it means it exceeds the pump's maximum voltage and it's too high and it must be decreased. To decrease the voltage, you could reduce the number of panels in series. All of this then gives us our array Pmax, which we then need to adjust based on the array efficiency. So that's in step 5C, where we get to estimating water production. If you need to, you can use this optional calculator to determine the array efficiency for specific conditions. But in this case, the design engineer estimates 88% efficiency. And then this automatic calculator, or this automatically calculates our estimated hourly water production based on the hourly flow rate, which is all based on the solar array's power output. So we can see from the sum in this column, we get an estimated daily water production from solar of 39.4. We can see this represented visually in the hourly production and motor power chart here, as well as the hourly water production chart here, which shows what the flow rates will be at various hours of the day, where the flow rate intersects our pump curve based on the power that we get for that hour of the day. So finally, we have a design check. We want to make sure that our cooling flow rate, minimum cooling flow rate is maintained. We're going to check the hourly water production and the allowable yield to make sure that our flow rate is not exceeding the allowable yield. And then finally, we want to check to make sure our daily water production is exceeding the design demand. And the percent difference here shows if it's a positive or a negative percent difference. And generally, you want to be within negative 5% to positive 20% of the daily water demand. So in summary, we get the number of panels in series, the number of parallel strings, the nominal size of the solar array in kilowatts, and the estimated total daily water production. So this is the end of step 5 and the end of the design process. I hope you enjoyed these videos going through this example of a solar pump design. And as always, if you have any questions about this design tool, please feel free to reach out to a Charleston engineer. We're always happy to help. We wish you best of luck, and may God bless you in all of your work using this design tool.